Your FastMCP server keeps recalculating identical tool results, listing unchanged resources, and fetching the same prompts repeatedly, while you have no visibility into how often these operations could be cached instead. We'll implement TTL-based response caching that specifically targets tool calls, resource reads, and prompt retrievals, then verify its effectiveness using built-in statistics. The pattern uses in-memory storage by default, but you'll see how to configure persistent backends and per-operation settings for production use.
From FastMCP server middleware caching, import response caching middleware. Middleware equals response caching middleware. MCP, add middleware. Hash later, retrieve statistics. Stats equals middleware statistics. Print F total cache operations. Stats.
This demonstrates the middleware pipeline pattern applied to RPC response caching, specifically for model context protocol operations. The caching middleware creates a transparent layer that intercepts and stores responses for tool calls, resource reads, and prompt requests, using time-to-live expiration rather than event-based invalidation. The distinctive aspect is its operation-aware design that lets you configure caching behavior separately for different MCP operation types, while maintaining a clean separation from business logic. The pattern works by inserting a configurable caching layer into the request processing chain, where each operation type can have independent settings for TTL, included excluded items, and enable-disable flags. By default, it uses in-memory storage with global keys for list operations, which means shared storage backends may require explicit namespacing to prevent key collisions. The middleware collects comprehensive statistics through the storage layer, giving visibility into cache effectiveness across all configured backends without modifying the core request handlers. This approach solves the dual problems of performance optimization and cache management complexity in RPC systems. By centralizing caching logic in configurable middleware, you avoid polluting individual tool implementations while gaining production-ready features like persistent storage backends and operational metrics. The trade-off is the need to understand the middleware configuration model, but this is offset by the ability to add sophisticated caching behavior without touching your core business components. Let's break it down line by line.
From FastMCP server middleware caching, import response caching middleware.
This imports response caching middleware, FastMCP's RPC response caching layer that intercepts tool calls, resource reads, and prompt responses. It uses TTL-based expiration with in-memory storage by default, requiring explicit configuration for production backends like retrievals store, and collects statistics through the underlying storage layer.
Middleware equals response caching middleware.
This instantiates response caching middleware, FastMCP's TTL-based response cache for RPC operations. It handles caching for tool calls, resource reads, and prompt responses, using in-memory storage by default with no event-based invalidation. For production, configure separate TTLs per operation type and use persistent backends like disk store or retrievals store to avoid global key conflicts in shared environments.
MCP, add middleware.
This registers the TTL-based response caching middleware with FastMCP's RPC pipeline. It intercepts and caches tool calls, resource reads, and prompt responses using in-memory storage by default, with no event-based invalidation. For production, configure persistent backends like retrievals store and namespace list calls to prevent key collisions in shared environments.
Hash later, retrieve statistics. Stats equals middleware statistics.
This retrieves TTL-based cache metrics from the RPC response caching middleware. The statistics reflect actual cache behavior across all configured backends, including hit-miss ratios and eviction counts, while exposing the default in-memory storage limitations. No persistence across restarts and global key conflicts in shared environments. For production, configure separate backends like retrievals and explicitly set per method caching via list tool settings or call tool settings.
Print ftotal cache operations. Stats.
This outputs the RPC response caching statistics from the middleware storage layer, tracking hits, misses, and operations across all configured backends. The default in-memory store doesn't persist across restarts, and list operations use global keys that may conflict in shared environments without explicit namespacing. For production, configure persistent backends like disk store or RTI store and set TTL-based expiration per operation type. Caching metrics pattern. Response caching middleware in FastMCP 2 implements TTL-based response caching for RPC operations, automatically handling call list tool, resources, and prompts with configurable per method settings. List operations use global keys that may collide in shared storage backends, requiring explicit namespacing for multi-server deployments. The default in-memory storage evaporates on restart, making persistent backends like disk store or RTI store essential for production.
The cache that never invalidates becomes the truth that never was.